PhD at Stanford. Lester Mackey was his PhD supervisor, is now at Microsoft Research, and Sebastian Vollmer, who's currently at Warwick. And so, okay, so the problem that I want to solve is slightly different to what was discussed this morning. I promise there will be some non-reversibility in this, but the setup is very much the same. So we have some Bayesian inference problem, and so say we have some likelihood here for some data in Rn, say given the parameter x, and say we have a prior on the parameter space x, on the parameter x, then Bayes' rule of course gives us posterior distribution. And so typically what one wants to do is compute expectations, credible intervals, and what have you based on this. And of course the traditional challenge is that unless you've chosen a very specific prior, then you can't typically compute the normalization constant. And typically your parameter space is quite high dimensional, so that's a very expensive integral to compute. And so that of course motivates Markov Chain Monte Carlo. And so the idea is that suppose we have a density pi, which would be in this case the density of our posterior, then there are various ways to construct a Markov chain, which will give values x1, x2, x3, etc., such that if we were to look at the empirical distribution, which is generated by the samples, then that will converge weakly to our target distribution P, which has density pi. And so for many nice posterior distributions, for many nice densities pi, MCMC practically provides a black box method to generate samples. And so once we have this, then one can use ergodic averages to approximate all the integrals that we want. And the good property is that MCMC is typically asymptotically exact. So what that means is that you can get arbitrarily accurate samples of your target probability distribution if you're willing to spend enough computational effort, in particular if you generate enough samples. And of course that comes at a price that MCMC typically has very, very slow convergence. And I would say so for many problems, for example, in large-scale engineering, chemical engineering, MCMC is not really a practical tool. So the problem is basically, especially in cases when the likelihood is very expensive to compute, it's really too slow to get anything useful within a reasonable amount of time. And so this has motivated, of course, various approximate inference methods where you're willing to sacrifice a little bit of bias, so you'd have some asymptotic bias, but the benefit that you win from having that asymptotic bias is that your sampler is much, much faster. And so a caricature of such an approximate inference method would be this. I think it's a pasta machine, I'm not sure. But basically, you have your target distribution P, you have a knob here, which is determined by a hyperparameter, which I'll call epsilon, and you crank the shaft and samples will come out, and you hope that those samples, that the empirical distribution that comes from those samples will converge to your target distribution. And so this knob here, this hyperparameter, is something you can tune, and it has really two extremes. So on one extreme, your scheme is very, very accurate but slow, and so it mixes very slowly, but it mixes to the right thing. In the other extreme, your scheme, your sampler, or your Markov chain will mix very rapidly, but it will converge to the wrong stationary distribution. And so, one example to consider in the big data scenario is stochastic gradient Langevin descent, which is pretty much falls into this type of model here. And so, if you have a fixed computational budget, it's not clear how you would choose your hyperparameter epsilon. So do I tune my parameter so that it converges very rapidly but to the completely incorrect distribution, or do I tune it in such a way that it converges more slowly but towards the right thing? And so tuning that is quite a challenge. And so if we were to use maybe some of the standard methods for tuning, we would say, okay, so let's look at the effective sample size as a method of tuning. But the effective sample size just measures mixing. And what it will do, it'll tell you, okay, just choose it to be as inaccurate but fast, because that's what's going to maximize the effective sample size. And so if you have a bias scheme, using ESS is not going to work to tune your hyperparameters. However, what we would really like is that if we had some really useful computational measure or computable measure of some divergence or distance between this ensemble distribution Q, or Qn, and the target probability distribution P, which is typically only known up to a normalization constant. So if we did have such a thing, how would we tune? Well, we basically do a grid search. So for a fixed epsilon, we'd generate some short exploratory runs of our chain, x1 to xn, which depend on epsilon. We'd generate the empirical measure, and then we'd basically compute the distance and choose the epsilon which minimizes this distance on average. So that would be a very reasonable way to measure, which is able to account for both the variance caused by not mixing, by not going far enough in time, as well as the bias that arises from having some discretization error, for example. And so more generally, one can ask the question, okay, so if I have some probability distribution P with, say, density pi on Rd, suppose I have an empirical probability distribution Q. So firstly, what is an appropriate measure of divergence or distance between P and Q? And that's not automatically clear on its own. But the second question is, can we choose one such that we can actually compute it? Or can we come up with some computable quantity which is equivalent to it in some sense? And so typically for Bayesian inference, the challenges are that the sample space is very high dimensional, and we only know the density up to a normalization constant. And you can rephrase the same question for example, for molecular dynamics problems. So the first question we have to ask is, what is an appropriate measure of distance? And if we're interested in Monte Carlo methods and Bayesian inference in general, I guess what we really want is that an expectation with respect to the empirical measure approximates well the expectation with respect to the target distribution P. And so based on that, we could say, all right, we can define the so-called integral probability metric, which is basically the maximal discrepancy between the two expectations over a class of functions H. And so in general, this is a pseudo metric. If you take H to be large enough, it's a proper metric. And so if you take H sufficiently large, it actually is as strong as weak convergence. And so different choices of H will give rise to different measurements of distance and different topologies. So for example, if I take a very large set, namely all the functions H which map into -1, +1, say, for example, and are measurable, so that's a pretty big set, then this defines a metric, and the topology it induces is equivalent to the total variation metric. And that is a very bad choice for your distance, because it's too strong. And so it'll always distinguish between a density and an empirical distribution. And so it won't capture things like central limit theorems. It won't capture any, it's definitely not applicable for our application here. Now, if you take H to be the set of functions which are Lipschitz, and the Lipschitz constant is less or equal to 1, then of course we get the Wasserstein metric, and so that's a reasonable choice. And of course, if we take something smaller, we take H, which is bounded Lipschitz, such that the distance plus the Lipschitz constant is less or equal to 1, then we get the so-called Dudley metric. And so the Dudley metric metriizes weak convergence. And on the other, or the Prokhorov metric, it's equivalent to the Prokhorov metric. And so the problem with choosing Dudley metric is that it's too weak. So in some sense, it's very insensitive to small perturbations, but then once your two measures, P and Q, kind of move away from each other, all it can tell you is that, look, they're far away, but we can't really measure how far. On the other hand, the Wasserstein metric is a good, for MCMC at least, it's a good kind of interpolation between the two of them. So for our choice, we would ideally like to compute the Wasserstein metric. So what we would like to compute is this quantity here. Now, of course, to compute this in practice is quite a challenging problem. So the first thing is that, remember, P is a measure on a very high dimensional space. And in particular, we can't really compute expectations with respect to P. If we could, we wouldn't be doing this from the start, right? So first thing we want to do is we want to be able to kind of rephrase this or control this by something which doesn't depend on expectations with respect to P. The second problem is that we're taking a supremum over an infinite set of functions, and that's something that we have to resolve as well. But at face value, this is not a computable quantity. However, we can bound it above and below by a computable quantity, and that's kind of the objective of this talk. So how do we do that? Well, for the first thing we want to do is remove that expectation. And so to do that, we can use Stein's method. And so this is named after Charles M. Stein, who unfortunately, sadly, passed away last year. And so he has his name on many different things in statistics, of course. For if you're interested in empirical Bayesian methods, then there's the James Stein's estimators. And so I think one of his most important works is the use of Stein's method to do Gaussian approximations of random variables, particularly Poisson. And so this kind of very simple idea that he originally had huge ramifications, especially if you're interested in things like functional inequalities. Stein's method plays actually a quite important role in this field. And so I'm going to give like a very general idea of what Stein's method is. So suppose we know, well, at least what it is in this particular context. So suppose we have this probability distribution P, which is known up to a normalization constant. What we do is we're going to find a set of functions G and an operator T, and I'll explain how to do that in a bit, but we need to choose them in such a way that if I take the expectation of Q applied to this, to Tg, then that is 0 for all G and G if and only if P is equal to Q. Now you might ask, how do I do that? I can show you, there's a very natural way to do that in a bit. And the second thing we require, and this is the more challenging one, is that for every function h in the set H, and H is the set of test functions, H is the set of test functions in my integral probability metric, there exists a G such that I can solve this equation. And this is the so-called Stein equation. And suppose I can do that without asking how, then if I take the expectation on both sides with respect to Q, right?
So the H is the whole space.
H is the space that we're taking the supremum here. Sorry, it's this space here.
Okay.
That we're taking the supremum over.
So does it just behave first?
It won't be, no. No. So in these cases, it's definitely not Hilbert.
Ah, you're right, yes.
So this is typically the H that we're considering. Okay? So if we take the expectation with respect to Q on both sides, then we get the expectation of expectation of H with respect to Q minus the expectation of H with respect to P is equal to the expectation with respect to Q of Tg, right? And then if we take supremum over all functions in H, we get the following bound. So we can bound above our discrepancy, which for our choice of H would be the Wasserstein distance, by this functional here. In fact, we call this the Stein discrepancy. And so this is a very important quantity. And so the classical Stein's method was actually applied when the probability distribution was a standard Gaussian on R, and the choice of the Stein operator was the following. So it's this expression here. And it kind of seems to be pulled out of thin air. And it will be until I kind of provide a different way of looking at it. But and then so one had to choose. So here the objective is to bound the distance between some probability distribution and the standard Gaussian. And so the question is, how do we choose this space of functions G? And to do so, one can use the following lemma that says that for every function H which is Lipschitz, there exists an absolutely continuous function G such that this Stein equation has a solution. And moreover, the solution has first, second, and third derivatives which have these bounds. And that's really convenient because all the bounds are in terms of the Lipschitz constant of H. And remember, our set H is the set of functions which have Lipschitz constant less or equal to 1. So all these bounds here are uniform, right? They don't depend. So to choose our G, we would just choose this set of G here, which is just, we replace H Lipschitz by 1, and we get this bound here. So then we know that the Wasserstein distance is less or equal to the supremum of this function here, which is just expectation of Tg over this set G here. And once we do that, we can do a lot of interesting things. So like the classical example is in some sense a weaker form of Variance. If we have x1 to xn which are independent with mean 0 and variance 1, and you have finite third moments, then you can actually bound the error between this error and the Gaussian distribution in Wasserstein distance. So it gives you a quantitative CLT, right? So this is This is a classical result which follows immediately from this bound here. And so that's for when you have a standard Gaussian, right? So the question is, how do we do it in general? And for me, this is the beautiful part of this theory. So if we set, we have this function g right here. So if we set g to be f prime, then the Stein operator looks like this. And so if you work in statistical mechanics, you'll definitely realize what this is, or at least certain classes of statistical mechanics. This is the infinitesimal generator of the Ornstein-Uhlenbeck process. It's a standard Ornstein-Uhlenbeck process. And the interesting thing about the standard Ornstein-Uhlenbeck process is that it's ergodic with invariant distribution, which is the standard Gaussian. And so this kind of led to a revelation that if you have a general probability distribution P with sufficiently nice density, then one could find, if one just produces a Markov process, say ZXT, which is ergodic with respect to the target distribution, then its generator should be a good choice as a Stein operator. So, in fact, that's what we do. You take a very nice Markov process. You have absolute control of whatever it is. It doesn't really matter where the Markov process comes from, as long as it's ergodic with respect to the target distribution. And then we have this nice property that the expectation with respect to Q of the generator applied to any function in the domain of the generator is 0 if and only if P is equal to Q. And that's the property that we wanted. And this is true for any sufficiently smooth density pi, or P, sorry. Okay, so and it's worth mentioning that the process Z that we choose doesn't need to have any relationship to, for example, the MCMC algorithm where these samples came from. They're completely unrelated. And so it makes sense to choose the nicest possible process which is ergodic with respect to our target distribution. And a very nice choice is the diffusion process. So we can in particular take an Ito SDE, right, of this form. So this has this infinitesimal generator here. And so in particular, it doesn't have to be, it can either be reversible or non-reversible. Unfortunately, our theory is a bit limited in the sense that we have to assume that the generator is elliptic. So this has to be positive definite. Hyperelliptic is still a bit open for us. But so the question then is, all right, so you come along with this probability distribution P with density pi. How do I choose B and sigma to be ergodic with respect to P? And so there's this very nice theorem, which, sorry, I should have attributed this. So this is actually a very classical result, but in this form, it was written in this paper called A Complete Recipe for Stochastic Gradient Langevin Dynamics. It was by Fox and Chen, I think. It was a recent paper in the machine learning community. But basically what it says is that if I have this SDE here with drift coefficient B and diffusion coefficient sigma, then pi is a stationary distribution of ZTX if and only if I can write the drift in this form here, right? Where sigma is basically the square of this. Grad log pi is the target distribution. Sorry, it's the log likelihood. This is the derivative of the diffusion tensor. And we have this vector field gamma. And so if gamma is 0, the SDE is reversible. If gamma is non-zero, then the SDE is non-reversible, irreversible. But what has to be satisfied is that this divergence-free condition has to be satisfied. And so that's all well and good. That, in some sense, this is a very classical result. But the interesting observation is the following. It's crucial for us that if gamma satisfies some other growth relations, then we can always write gamma in this form here. So we can always write it in the form of this weighted divergence of this matrix function C, where C is skew symmetric. And in that case, we have this lovely representation for a general diffusion process. And I think that's very nice. So here, sigma will be a strictly positive definite matrix function. And that captures the reversible dynamics. And this matrix function C is skew symmetric, which captures the non-reversible dynamics. And so that's what we're going to work with. And so we have this generator here. And so like we did with Stein's method, we identify G with the gradient of U. And we use this particular representation here for our Stein operator. And so that's our choice of of the Stein operator that we'll work with. And so we can play around, right? We can choose different values of sigma and C, and we can recover some very well-known diffusions. So if we choose sigma to be identity in C is 0, you get the standard overdamped Langevin. If you choose sigma to be identity in C non-zero to be a constant, then you get standard overdamped non-reversible Langevin, which we've done some work with in the past. Of course, if you take sigma to be like some matrix P, which is constant positive definite, then you get a precondition overdamped Langevin. And of course, you could also, if you allow sigma to be not positive definite, you can easily recover, for example, second order Langevin as well. But our theory doesn't cover that completely, so I won't mention it. Okay, so that's fine. We have our choice of operator. Our Stein operator is now done. So now the hard part is how do we choose this set of functions G? And so if you recall, we have to choose a set of functions G such that for all h in H, and remember H is the set of functions which are Lipschitz with Lipschitz constant lesser equal to 1, there exists at least one G in G such that it solves the following Stein equation. Now, remember that we always identify the solution G in terms of grad U, right? And so what we need to do really is we need to solve the following Poisson equation for UH, which is given by this. And so this is a very, very common problem. If you're solving, for example, central limit theorems, you'll always come across this type of problem here. And kind of the crucial trick that one needs to identify is that you can always write it in in terms of this integral here, where so basically it's the integral from 0 to infinity of the expectation with respect to P of H minus the semigroup PT applied to H, where PT is the semigroup associated with your process. And this is effectively just relating the Green's function for the Poisson equation to the Green's function for the corresponding heat equation or parabolic PDE, right? It's just the usual duality between those two. And so what we need to do now is we need to basically identify in which space this function lies, right? And so we need to do two things. We need to handle, so what we need is essentially a regularity result. And so we need to do two things. We need to handle what happens when in this integral, when we're in the region close to 0, and we need to handle what happens at infinity. And so to do this, for small t, we need to use regularity results. We use, in this case, we used Bismuth-Ellsworthy Lie type formulas for the derivative of the semigroup, and we have to control it. And these become, when you take derivatives of this semigroup with respect to the initial condition, they become singular for small t, and you have to really carefully control how that behaves near 0. And then in the other extreme, you have to deal with what happens as time goes to infinity, and you have to make sure that you can get the right decay of the semigroup for large t. And so there are two kind of ways to do this. If you're a probabilist, you'd say, okay, I'll use coupling arguments. So for example, the results of Air-Berlet, for example, which is what we followed. We have to make some assumptions, such as distant distributivity. If you're an analyst, you can use different assumptions like the curvature dimension condition and use local Poincare inequalities. Effectively, they're almost equivalent. So we chose the former. So if we do that, then we can kind of get the first result, which is kind of crucial, which identifies our set G. So the results are following. We assume that in addition to the properties we had before for our process, we assume that the process satisfies a Wasserstein spectral gap, which is of this form. And all this says is that if we take our process Zt starting from two measures, mu and pi, and we let the process evolve from that initial condition, then the distance between the resulting measures will contract with rate r of t, where r is some integrable function. And if that condition holds, then we have this result, which basically says that if we take a function h, there exists a unique function u of h to the Poisson equation, such that the solution has mean 0, and u is smooth, sufficiently smooth. And the most important thing is that we have this bound. So the gradient of u is bounded by the Lipschitz constant of h, and if we have some more regularity and smoothness, then the Hessian of u is also bounded by the Lipschitz constant of h. And remember, the Lipschitz constant of h in this class of functions is always less or equal to 1. And moreover, the value of k we know explicitly. It's an explicitly computable quantity. So with that in mind, using the intuition from the classical Stein method, we might be tempted to choose this g here. So it's the set of functions g in C1 such that it's bounded such that the L infinity bound is less or equal to 1 and the gradient is less or equal to 1. Sorry, this would work, right? But the problem is that there will be other problems later on with this particular choice. In particular, it's a bit too large. And what will happen is if we would get cases where the Stein discrepancy doesn't go to 0 for two measures, for a sequence of measures, but the Wasserstein distance will, right? And we don't want that. We want those the Wasserstein distance and the Stein discrepancy to be equivalent in some sense. So one will go to 0 if and only if the other goes to 0. And so because of that problem, we instead choose the classical Stein set here, which is a little bit smaller. So basically we add this additional condition here, which is that the gradient of g is Lipschitz with Lipschitz constant less than 1. And immediately we run into a problem because the solution of the Stein equation is not contained in this set for any rescaling of the set. And so what we have to do is have to cheat a bit. We mollify the solution, we smooth it, and that will work. And you can play around with it, and you basically can get the result that you want, but you lose something. So we can summarize it in the following two results. So if we assume we have this process Tx like we described before, and we have some conditions on the coefficients, which basically are regularity conditions, meaning they're sufficiently smooth, then there exists an explicit constant L such that the Wasserstein distance is controlled by the maximum of the Stein discrepancy and the square root of the Stein discrepancy. And what that means is that when the Stein discrepancy is very large, there's effectively a linear bound between the two, but as it goes to 0, the square root will kick in, and you get a sublinear bound. More specifically, you get a square root relationship between the two. If you assume a little bit more regularity, then you can make this relationship a little bit tighter. Basically, you can make the second part arbitrarily close to linear, right? So for every iota, you can find a constant L iota such that this bound holds, and this term here can be made arbitrarily close to 1, but never actually equal to 1. So that's really as close as we can get with this theory. And if you add more assumptions on your drift and diffusion coefficient, you don't get anything else. So this seems to be quite tight in that sense. And so, okay, so that's one part of the question. We've basically said, okay, if we choose this Stein operator and if we choose this set of functions g, then if the Stein discrepancy goes to 0, so this guy goes to 0, then sorry, that should be a g there. Don't know why it's an f. I don't know why that's an f either. If this guy goes to 0, then Wasserstein distance will go to 0. But of course, we want those to be equivalent. So the natural question then is, if the Wasserstein distance goes to 0, does the Stein discrepancy go to 0? And the answer is, if we have some additional constraints on the diffusion coefficient that we choose, and remember, this is something that we choose ourselves, it's arbitrary, it's not related to the dynamics of for example, our ensemble distribution, then yes, we also have a bound from above. And so basically, assuming all the conditions I just mentioned hold, the Wasserstein distance is dominated by the Stein discrepancy, meaning that if this goes to 0, this goes to 0, and conversely, Stein discrepancy is dominated by Wasserstein distance. So if one of them is small, the other one has to be small, basically, which is really what we want. Okay, so that's, we've basically described what the Stein discrepancy is, but we really haven't said how we compute it. So now we really need to exploit the fact that Q is an ensemble distribution over finitely many points. So I assume that we have these weights Q here, which I didn't have before, and that we can write the ensemble distribution in its form. And then, if you remember, the Stein discrepancy was this supremum, right? Of this objective function, and so this is our choice of, this comes from our Stein operator, and this is the expectation with respect to Q. And remember, we had the set, we're taking the supremum of the set G. And the G was the set of functions which satisfies these three inequalities here. And so the problem is that, although this is a perfectly easily computable quantity, the constraints are infinite, right? We have infinitely many constraints because we have a constraint for every single value of x. This is a problem, right? So this is not an optimization problem that we can solve on a computer. And so it's basically an infinite dimensional problem with infinitely many constraints. So that's something we need to fix. And so one idea is that instead we come up with another Stein set G, right? which has equivalent convergence properties. And so what one does is you define a graph of vertices and edges on RD, and we define the graph Stein set to be the functions g, where we have the same constraints, but those are only imposed on the points x1 to xn. So we would have the maximum of g and its gradient less or equal to 1 only on the vertices. So the vertices would be x1 to xn. And similarly, the constraints on the derivatives would only be imposed in the finite difference form. So between x and y, where x and y are two values in the set x1 to xn. And similarly, we do that for the higher derivatives. And so this is, instead of infinitely many constraints, we now have a problem which has many constraints, but it's a finite number. And to be more precise, we have order v plus order e constraints, right? So we have these constraints which are just at the vertices, and then for every pair of edge, for every edge, we have these other constraints, right? So that's order v plus order e. And so we can define a Stein discrepancy for all functions g in this set. And so that makes perfect sense, but we don't know what the equivalence is between the different Stein discrepancies. And so the following result kind of tells us that we can actually use one instead of the other. So to be more precise, if g is the complete graph over x1 to xn, where these are our samples, right? Then, so the Stein discrepancy for our previous over our previous set is bounded above by the Stein discrepancy over this finite set of constraints. And in some sense, this is a trivial bound, right? Because this just comes from restricting a function g here to a function over the vertices, and that's all well and good. But the crucial point is that this Stein discrepancy here, this graph Stein discrepancy, is bounded above by the actual Stein discrepancy. And to be able to do that, we require a very deep theorem from analysis, which is basically the Whitney extension theorem, which tells us that if we have a function which has constraints on finitely many points, there's just an extension to that function where the similar bounds are satisfied over the entire state space. And so this lets us reduce a problem, an optimization problem over infinitely many constraints to an equivalent optimization problem over finitely many constraints. Of course, the problem is that it's still n-squared constraints, right? So this is still a very expensive optimization problem. However, and this is something I'll skip, there are ways to kind of reduce it even further, and one can get closer to like n log n, for example. Okay, so I just want to give one very quick example, and I'll leave you there. So let's take one kind of recently, well, not so recently now, developed approximate inference method is stochastic gradient Langevin descent. And so the idea is that if you have problems where you have lots of data, right, you can't really compute the gradient of along likelihood at every step. And so what you do instead is you basically you don't do a Metropolis-Hastings correction, you do an Euler-Maruyama discretization of your Langevin equation, and at every step, rather than compute the full gradient, which is too expensive, you take some subset of the gradient, subset of the data points, you compute a gradient based on that, and then you move a step. And so the length of the step that you move is dependent on this step size parameter epsilon. And so when epsilon is small, you get very slow mixing, but the error, the bias, the asymptotic bias is very small. When epsilon is very large, then it mixes quite rapidly, but it's not clear what it's converging to, right? There's large discretization error. And so if we were to go by ESS, effective sample size will tell us, just make it mix as fast as possible. We don't really care about the bias. It's not able to see bias. So what we do here is we took this kind of double well type distribution, and so using some exploratory samples, we looked at the effective sample size and this Stein method for different values of the step size epsilon. And so, as I said, the effective sample size is basically saying, oh, you should make the step size as large as possible because it mixes very well. But the Stein method is saying, no, this is kind of the sweet spot here. If you do it more than, if you choose larger step size, then the bias will be very large. If you choose smaller step size, then you're not going to mix rapidly enough. So this is kind of the best point. And so here, what we illustrate is that the long time simulation, if we take epsilon to be here, right? And so both of them say that the the stationary distribution is not going to be very good. In fact, it really hasn't mixed well enough. It hasn't explored the state space well enough. If we take the step size to be epsilon is 5 e to the minus 2, so that corresponds to this point here, then the ESS is basically the best here, while Stein is not so good, and we see this long-time simulation which doesn't really reflect the stationary distribution that we want, the target distribution that we want. If we take the point here, which is optimal for Stein, then we see that we get a good kind of agreement between the two, and that suggests that this is a good choice. So that's basically the idea. And thank you for your time.
Thanks, Andrew. Any questions?
So can I ask, maybe the yourself and reading it, but why can you do it only elliptic?
Yeah. It's not that you can only do it in elliptic, it's that we only know how to do it in elliptic.
What was
So I mean, there are two steps here, right? So for the first part, let me go back. Where was it? Actually, this is what we need. So of course, if you assume it's hypoelliptic, right? That's fine. You can get, with some additional conditions, you can get decay for large t. But then, once you try and get, explicit regularity results, like results on the derivative of the semigroup and second derivative of the semigroup, things get quite difficult. And so we weren't really able to follow through with the calculations.
It's the derivative of the semigroup.
Yeah, it's the regularity for small t. I'm sure someone will come along and publish a paper which will solve our problem and make us very depressed, because we did try this for some time. But as it stands, this is out of our reach. So it's an open problem for us right now.
But would it make sense to do it, or you think that there is no gain?
No, there is probably gain. So even going from so I mean, you would say, what's the point of all these different diffusions? Just choose this one. I mean, it works perfectly fine. But what we observe empirically, without any justification, is that if you choose non-reversible Langevin, the Stein operator based on non-reversible Langevin, then the constant between the two kind of Wasserstein and Stein discrepancy appears to be tighter. So there's a tighter relationship between the two, and that's good, right? You want those two to be as close as possible. But we don't really have, there's no real justification why that's the case.
Perhaps you said that also when you talk about the stochastic gradient descent of Wasserstein,
Yeah.
actually the epsilon step size change in the algorithm, right?
Oh no, I mean.
Yeah, because first they do metropolis acceptance on big steps, and then when they reach another regime, they do like little steps, and they always accept it.
You mean decreasing steps?
Yeah, it was decrease epsilon, and so your ideal epsilon, it matches the transition or not?
To be honest, we've kind of so forgotten about the decreasing steps, because in practice you never could do that, right? So what we say is we just fix it and tune it. So I haven't really compared to what is suggested in the paper. Oh, I should have. That's true.
Any other questions? Well, thanks again, Andrew.
Okay.